Well, hello, ladies and gentlemen. Let's proceed on. We pretty much have finished up our discussion of air standard, closed, and open systems. So we're not going to be using air anymore. We're going to shift gears and look at cycles involving vapor, liquid, and mixtures of vapor and liquid. So we're going to be looking at vapor, power, vapor compression power cycles. So we're going to be using H2O as the working fluid instead of air. Basically, what we're going to be doing is looking at power plants, how power plants work. Power plants utilize H2O typically as the working fluid. So they use a combination of pumps, turbines, furnaces, boilers, condensers. They use a combination of devices to utilize H2O as a working fluid to produce power. So we're going to shift gears today and look, instead of air as the operating fluid, we're going to look at devices that use H2O as the operating or working fluid for the cycle. Okay? So to that end, we're going to start off by looking at the most basic vapor power cycle, which is a Carnot vapor power cycle. Basically, we're going to put a Carnot cycle inside a saturation dome. Okay? And use H2O as a working fluid. Then we're going to modify the Carnot cycle, make it a bit more technically plausible, technically feasible. And the result will be a Rankine cycle. Rankine cycle, R-A-N-K-I-N, Rankine cycle. So we're going to take a Carnot cycle, which is operating inside the saturation dome, and we're going to produce the Rankine cycle after we modify it. Okay? Now, a new device is going to crop up when we have the Rankine cycle. Instead of having a compressor compressing H2O, we're going to have a pump. What's the difference between a pump and a compressor? Well, pumps raise the pressure of a liquid, and compressors raise the pressure of a gas. So we're going to have, in this Rankine cycle, we're going to have compression. We're going to have the increasing pressure of water. We're going to be pressurizing water, so we're going to be introducing a pump into the device in the place of a compressor. So we need to talk about how to calculate pump work. What's the work required to increase the pressure of a liquid, let's say reversibly? So what's the work required to increase the pressure of a liquid reversibly? In other words, what's the expression for reversible pump work? Reversible pump work. So we'll talk about reversible pump work. And then we'll move on and do an example of a Rankine cycle. Not an ideal Rankine cycle, but one that's very similar. And this Rankine cycle is going to have multi-stage expansion, in other words, multiple turbines, and will involve superheating of the working fluid, the H2O. You'll see what this is about when we get to it. Okay, let's get started here. Let's talk about the simplest vapor power cycle we can think of, which is the Carnot cycle operating inside the saturation dome. So the Carnot vapor power cycle. So you remember the Carnot cycle, you have the TS diagram right here. The Carnot cycle involved two isothermal and two isentropic processes. So it looks just like a box or a rectangle. So we have the heat coming in, we have the heat coming out, and the remaining processes are adiabatic. Okay, so that's the Carnot cycle. If it goes in the clockwise direction, then it is a work-producing cycle. If it goes in the counterclockwise direction and the heat flows are in the opposite direction, it is a refrigeration device or a heat pump, i.e. a work-consuming device. Okay? Now, one way to get this device to work, one way to envision this device is to actually put it inside of a saturation dome. So maybe I should do this in a different color, but here's our dome right here. So here's our dome. So here's our saturation dome right there. And we can see that the isothermal heat addition and rejection processes are necessarily isobaric because we are in the saturation dome. So there are some isobars that go through here. So here's this isobar. So here's our P-min isobar. And here is our P-max isobar. And so provided the heat addition and rejection occur at constant pressures, P-min and P-max, they will necessarily occur at constant temperature so long as we're inside the saturation dome. Okay? So as long as the heat addition process in some kind of a boiler and the heat rejection process in some kind of condenser, and we'll talk a little bit about that in a moment, as long as those devices are isobaric and we're inside the dome, they're necessarily isothermal. So the efficiency of this device has the hope of mimicking the efficiency of a Carnot cycle. Okay? Now, there's problems here. There's some problems here. So what are some problems with this cycle? What are some problems with this cycle, some deficiencies? Well, the primary deficiency with this cycle is during the compression process we have here. The compression process. What we have here is we have at low pressure a mixture of vapor and liquid, saturated, and then we're compressing it all the way up to a saturated liquid. Now, most mechanical devices, open flow devices, do not like mixtures of H2O, of a liquid and vapor. A compressor is made to compress a gas, and a pump is made to compress a liquid, and there aren't really any good devices that handle both together. So the compression process, from state 1 to state 2, let's say, the compression process 1 to 2 will result in significant mechanical damage to a compressor or a pump, because we have a mixture of the two, to a compressor or a pump. A pump is meant to pressurize liquids. Compressor is meant to compress vapor or gases, okay? So that's the primary. There are some other objections here, but they're not so bad. But that's the primary objection to this Carnot cycle within the saturation dome. The process 1 to 2, which is the compression process from P-min to P-max, it's not easy to develop a device which can compress a mixture of liquid and vapor up to a saturated vapor. Not easy to build such a device. Okay, so what are we going to do? We're going to replace process 1 to 2, keep everything else, but we're going to replace process 1 to 2 by cooling the mixture at low pressure all the way down to a saturated liquid. And then we're going to compress, we're going to increase the pressure of the saturated liquid up to Pmax in a pump. So we're going to replace, so what do? We replace compression process 1 to 2 with a pumping process 1 to 2. Let me show you the TS diagram for this new cycle. Temperature, specific entropy, saturation dome. Here's our minimum and our maximum pressure in the cycle, P min, P max. Okay, so instead of starting off at state 1 as a mixture, instead of starting state 1 as a mixture of saturated vapor and liquid, we're going to start off as a saturated liquid instead. We're going to start off as a saturated liquid. So state 1 is going to be right here. Now, if the compression process is isentropic, in other words, reversible adiabatic, then 1 to 2 looks like this. Okay? We start off with a saturated liquid and go to a supercooled liquid. So we're out here to the left of the dome. And then we add heat all the way up to where the supercooled liquid becomes a saturated vapor. So this is state 3. And then we expand the saturated vapor to a saturated mixture in a turbine at state 4. So we're adding heat, Q in, doing pump work, turbine work, adding heat, rejecting heat, 4 to 1. Let me show you what this device might physically look like, okay? So we're going to start off with a pump. A pump is a device that pressurizes, don't want to say compress, pressurizes liquids. So we start off with a pump. So we have a pump, and into the pump at state 1, we start off with a saturated liquid at low pressure P1. So P1 is P min. Saturated liquid at P min. Now we do some pump work. W dot pump. Okay? And we compress the saturated liquid up to a higher pressure, and we end up with a supercooled liquid. So this is a supercooled liquid up to state 2. Okay? And by the way, there's some mass flow rates for the H2O. There's some m dot H2O flowing through this pump. Okay, now we're at a higher pressure. So P2 is the maximum pressure, P max. And then we add heat to this supercooled liquid in a boiler. We take the liquid and we boil it away until it's a saturated vapor. So we're going to add heat, Q dot boiler. So this is our boiler. Typically, it's an isobaric boiler. There might be a pressure drop in the boiler, but as far as the ideal cycle is concerned, let's say there's no pressure drop in the boiler. And then we end up at state 3. And state 3 is a saturated vapor, okay? Saturated vapor, state 3. And now we expand. And now we expand the saturated vapor down to the minimum pressure. So again, we're at P equals P max. We're still at P equals P max. We expand in a turbine, producing a certain net turbine work. Now the turbine is going to drive the pump. And so the net work produced or power produced is W dot turbine minus W dot pump. Whatever is left over after we drive the pump is our net power, okay? So we expand the saturated H2O vapor, and we get primarily vapor, just a little bit of liquid, hopefully just a little bit of liquid. We get high quality H2O. So state 4 is a high quality steam. It's mainly vapor. There's a little bit of liquid in there, just a little bit at state 4, okay? Okay, now we got to get rid of the excess heat to complete the cycle. We pass the saturated mixture, high quality steam, at low pressure. By the way, P4 is back down to P min. And we reject the heat, Q dot out, and the Q dot out occurs in a condenser. We take a vapor and we condense it to a saturated liquid. So this is called a condenser. If you want to know how this physically works, basically, so steam comes in, heat gets rejected, and we get liquid saturated at the very bottom of the condenser. And that gets pumped back to the pump. Okay, that makes its way back to the pump. So this Q dot out is Q dot condenser. Okay? All right, so let's write out the processes here for the ideal Rankine cycle, which is just what we've been looking at. Ideal Rankine cycle. Ideal Rankine cycle. Ideal Rankine cycle. So process 1 to 2. Reversible, adiabatic, pump work. So we go from the minimum pressure up to the maximum pressure in the cycle using the pump. And then we have isobaric heat addition in the boiler. Isobaric heat addition in the boiler. So that is from 2 to 3. Isobaric heat addition. In boiler. And then from 3 to 4, 3 to 4, 3 to 4, we have expansion in the turbine where the power is extracted. Part of it is used to drive the pump. The remainder is available for use. So we have reversible expansion, reversible adiabatic, expansion in a turbine. And then once we leave the turbine, we have to go back to state 1. So we end up with a saturated mixture, primarily vapor, but just a little bit of liquid. We have to go back to the saturated liquid by extracting heat and condensing the vapor back into a liquid. So 4 to 1 is isobaric, condensation, or heat rejection in condenser. Isobaric, heat rejection in condenser. In the condenser, okay? So this is the ideal Rankine cycle. The TS diagram and the device diagram are given right here. So I'm going to write right up here, ideal Rankine cycle. This is the ideal Rankine cycle here, all right? So it uses H2O as a working fluid. We have phase changes going on. We're operating at times within the dome. Definitely not using air. Definitely can't use ideal gas law. So we're stuck with saturation tables, superheated vapor tables. Maybe you'll have a problem where we have superheat. Okay? Who knows? Who knows? So we're dealing with H2O. Now, what are some strategies here for increasing performance of the Rankine cycle? Remember we talked about increasing performance of the Brayton cycle? What are some things we can do to modify this cycle to either produce more power or to make it more efficient? So ways to increase performance. We're only going to talk about one or two here. The big one is to superheat the H2O as it comes out of the boiler. So the big one is superheat at boiler outlet. So the TS diagram there, TS, there we go. Ideal cycle. The key here is to get out in the superheated vapor region. Okay, so here's 1, 2, 3, and 4. So one way to increase specific work for the cycle is to superheat state 3, the boiler outlet. So add more heat in the boiler and force state 3 to be a superheated vapor. That's one way to increase the area. So as state 3 becomes more and more superheated, the area bound by the TS curve gets bigger and our specific work goes up for the cycle. In addition to that, superheating ends up increasing the quality at the turbine outlet and is better mechanically for the turbine. The less droplets, the less mist of liquid water in the turbine exit state, the better mechanically for the turbine. Okay? So superheating, the ideal Rankine cycle with superheat tends to increase the specific work over the cycle. Okay? It increases the cycle work or the net work. Okay? Tends to increase the cycle work. It can also, depending on the situation, increase the efficiency as well. So cycle-specific work and efficiency also go up, okay? So that's an obvious way to increase the efficiency of the Rankine cycle, the ideal Rankine cycle, increase performance of the ideal Rankine cycle. Another thing to do that is often a good idea, so efficiency goes up, specific work goes up. Another thing to do is to have multi-stage compression or expansion. So I'm just going to draw a picture here of multi-stage expansion. Remember we had in the Brayton cycle, we had the intercooler, the reheater, and the regenerator. You can do similar stuff to the Rankine cycle. I think we'll leave the regeneration part and the multi-stage pump part to a homework problem. But let me show you what you can do here with the expansion in the turbine. So we can do multi-stage expansion. So we can do multi-stage expansion and compression and regeneration, but let's just talk about multi-stage expansion. So in that case, let's draw the TS diagram for a Rankine cycle with superheat and multi-stage expansion. So here's the saturation dome. Here's our P-min. Here's our P-max. And here is some intermediate pressure. So PI, I'll call it, some intermediate pressure. So what we can do here is we can start off with reversible pump work all the way up to P max, add heat, superheat. So here's where Q boiler is right here. And then we can pass the H2O through a high pressure, followed by a reheater, followed by a low pressure compressed turbine. So we have expansion in the high pressure turbine. Then we have reheat. So we have Q reheat. And then we have further expansion. Maybe my diagram isn't the best here. I don't think we're going to end up quite as far out in the superheated vapor region here. But we can have multi-stage expansion in multiple turbines. The benefit of that is we can increase the specific work for the cycle by increasing the area bound by the TS curve. Okay? So you can increase output with multi-stage expansion. Nice thing about multi-stage expansion is it allows you to engage in multi-stage compression in the pumps, multiple pumps, with regeneration. So this allows you to also increase the efficiency if you include regeneration and multi-stage pump work or compression. Okay, I think let's move on here. This is just a lot of talk. Let's move on here. Let's talk about this pump work. The only thing that's really new here is this pump. What is this pump? How does it work? How do we analyze this pump? We know how to analyze compressors and turbines. That's pretty easy. But what's this pump all about? What's this pump all about? Let's talk about ideal pump work. Ideal, and if you like, reversible, adiabatic pump work. Reversible adiabatic pump work. Let me get some more chalk here. Reversible adiabatic pump work. We got to calculate W dot pump, so we need to figure out how to calculate specific work for a pump, especially a reversible adiabatic pump work. Okay, so let's say we have a pump. So here's this pump. Now this pump receives a liquid coming in, so this is state 1, and it forces out at state 2 also a liquid, and there's some kind of propeller or something in here. So there's a shaft in here, something to increase the pressure of the liquid. So we have W dot pump. Okay? The inlet is going to be state 1, the outlet is going to be state 2. The inlet pressure is P1, the outlet temperature pressure is P2. And of course, there's some mass flow of going through this pump. Okay, there's some mass flow m dot. All right. Also, there's some sort of an inlet temperature. Let's say T1. Okay. Now, this thing is reversible and adiabatic. So, reversible adiabatic. So, it's insulated. Let's apply the entropy balance and see what we get with a reversible adiabatic pump. Reversible adiabatic pump. If your gut intuition that it's an isentropic pump, you're absolutely right. So here, S balance, we got, so see, for an open system, we have the sum of Q dot over the interaction temperature. So my pump, here's my open system pump. So Q dot is equal to ds within my control volume dt plus the sum of the mass flows times S out minus the sum of the mass flow times S in, and then I've got S dot gen, okay? Open system entropy balance. So it's adiabatic. I think we're going to assume steady state here, and every single problem we've done has been a steady state problem. So this is going to go reversible. Single inlet, single outlet. So we got m dot S2, m dot S1. And so I get the mass flow rates are the same going in and out if you apply the mass balance. So I get 0 equals m dot S2 minus S1, or S2 equals S1. It is an isentropic process. If it's reversible and adiabatic, it's isentropic. Okay, nothing big going on there. Let's apply the property relationship. Let's apply the property relationship to my liquid that flows in and out. Remember, a pump compresses liquid, raises the pressure of liquid. So I'm going to say here, note, this is some kind of a liquid. I guess state 1 is a saturated liquid, and state 2 is a supercooled liquid, okay? Okay, so let's apply a property relationship. Well, one of them is ds is equal to cv dt over t plus, let's see here, oops, kind of getting ahead of myself here. I was going to write IGB, and that's absolutely not true. So I guess I better go back here. Let's write the original TDS equation. Let's write the TDS equation. TDS is equal to du plus PdV. So that's a property relationship that we derived all the way back in chapter 6. It's a property relationship. So this is true in general. Prop relationship. It's due everywhere and anywhere for any substance. Now, if we have a liquid, is a liquid compressible? In theory, no. I suppose you may be able to compress it just a little bit if you crank the pressure up by a huge amount. But the idea here is that a liquid is approximately incompressible. So for an incompressible, the differential change in specific volume is 0. Incompressible liquid. Saturated or otherwise, a liquid is approximately incompressible. So the dV term is 0. So I get TDS is equal to du. So I get TDS is equal to du. And using a property relationship, I get specific heat times the differential change in temperature. Remember, for an incompressible, I can write CV or CP here. It doesn't matter because there's no boundary work going on because it's incompressible. So I'm just going to put a specific heat there. If you want to put a CV here, fine. If you want to put a CP here, fine. They're both the same for an incompressible or a liquid. Okay, so let me solve for ds. ds is equal to c dt over t, or delta s from 1 to 2 is equal to the integral of the specific heat dt over t from T1 to T2. Okay, so for this process with an incompressible, delta S is equal to integral Cp dt over T. Now, what is delta S? what is delta S for this process through the pump? It's reversible adiabatic, therefore delta S is 0. It's an isentropic process. So delta S is 0 because it's isentropic. So this thing is 0. Therefore, getting a little cluttered here, but try to follow along. If this integral is 0, it means that this temperature change is 0. That means T2 is equal to T1. So for adiabatic reversible pump work, there is no temperature change from the inlet to the outlet. So isentropic process. So we have delta S from 1 to 2 is 0. And we have, strictly speaking, T2 is equal to T1, strictly speaking, if we have no change in volume whatsoever in our pump. Now, I'm going to fudge a little bit. Liquid is slightly compressible. If I really crank down on the pressure, I can get a small change in volume. So instead of writing T2 is equal to T1, I'm going to say, but liquid may be slightly compressible. Therefore, T2 is approximately equal to T1. Maybe real liquids in real life, you can compress them ever so slightly with large pressure changes. So we're going to say T2 is approximately equal to T1, or if you like, delta T from 1 to 2 is approximately equal to 0. Okay? So as far as the TS diagram is concerned, TS, here's our dome. Here's state 1, which is a saturated liquid. Here's the P min and a P max isobar. These isobars are a lot closer together. There we go. That looks better. So there's state 1. State 2 has a very, very small temperature change. T1, T2. Very small temperature change going through the reversible adiabatic pump. Very small temperature change. Delta T is approximately 0. Okay. Now, next step, how do we calculate the work? How do we calculate the work for this reversible pump? We've established that the temperature change is minimal. How do we calculate the work? Specific work. Let's apply the energy balance. So let's apply the energy balance. We already have delta T from 1 to 2 is approximately equal to 0. We already got that. Okay? So how do we get the work? Let's apply the energy balance to this thing. We're going to get W dot pump is equal to M dot H2 minus H1. That's going to be our pump work, pump power. Okay? Dividing through by M dot, of course. And we get the specific pump work is equal to H2 minus H1. Okay, that's not very surprising. Let's expand the H's and take into account the definition of enthalpy, specific enthalpy. So this is U plus PV at state 2 minus U plus PV at state 1. Or if you like, U2 minus U1 plus PV2 minus PV1. Okay? Just expanding the definition of enthalpy, specific enthalpy. Now, for a liquid, delta U right here, delta U from 1 to 2 is equal to the integral of du, which is equal to the integral of specific heat dt from T1 to T2. Using a property relationship, du is equal to specific heat dt. It's actually CV dt. So delta U is equal to the integral of CV dt. Now, if delta t is equal to 0, then that integral CV dt is 0 as well. So this guy is equal to 0. Why? Because T1 is approximately equal to T2. So this whole term is gone because T1 is approximately equal to T2. Okay? So then I end up with the following. All I got left is the PV at state 2 minus pressure times specific volume at state 1. Now, if it's incompressible, that means that specific volume at state 1 is approximately equal to specific volume at state 2. So I can pull out the specific volume in this difference. So I get specific volume times P2 minus P1, or if you like, specific volume times delta P from 1 to 2. So, reversible specific pump work, W pump, is equal to a specific volume times delta P from 1 to 2. Now you might ask yourself, what specific volume should I use? If they're both basically the same, which is the easiest specific volume to use when I do calculations? I would use the specific volume of the saturated liquid. So I would use specific volume of the saturated liquid evaluated at state 1. So T1 or P1, okay? So V sat liquid times delta P from 1 to 2. So the expression for reversible pump work, W pump, and this is reversible pump work, is V sat liquid times delta P from the inlet to the outlet. Okay, put a little box, I'm sorry it's sideways. Put a little box around this, okay? That's your expression for reversible pump work. I will box this one up here to pump. Reversible, 1 to 2. I'm gonna put a little box around this thing. Okay, a little box around it, all right? Let me show you the process one more time. T, S. Here's the left-hand side of the dome. Start off with a saturated liquid, exaggerating. End up with a supercooled liquid. And so the reversible pump work is given by V sat liquid times delta P. Okay? All right, I think that's it with this. We'll move on and do an example involving a Rankine cycle. All right, ladies and gentlemen, let's do an example here of a non-ideal Rankine cycle. Let's do a non-ideal Rankine cycle with superheat. So what we have here, again, is a pump, adiabatic pump. a boiler, and of course, a adiabatic turbine. And then the condenser, and the working fluid, which is H2O, goes around in a loop, as you can see here. State 1 is a saturated liquid. We have some pump work going up to, going from P min to P max. So we start off at a P min, and we go up to a P max, which is P2, due to the pump work. And then we add heat in the boiler, extract energy in the turbine, expand the superheated steam, and then condense back to a saturated liquid in the condenser. Let me give you some numbers here. The minimum pressure in the cycle is 7.5 kilopascals. So we start off as a saturated liquid at state 1. The maximum pressure in the cycle is 6 megapascals. So we start off below atmospheric, less than 1/10 of an atmosphere, very low pressures. Basically, that reduces the condenser temperature when we have such a low pressure. Maximum pressure is 6 megapascals, and then we have pump isentropic efficiency of 80%. So the pump is not reversible. Isentropic efficiency of the pump is 80%. The isentropic efficiency of the turbine is 85%. And the total heat transfer into the cycle from the boiler to the boiler is 40 megawatts. 40 megawatts. So what are we supposed to find? Let's find the pump work, specific pump work, the specific turbine work, the net specific work, find the specific heat addition, Q boiler, into the boiler, find the thermal efficiency for the cycle, so W net divided by Q in, or Q boiler, find the mass flow rate. What's the actual mass flow rate? The rate at which H2O flows around in the cycle. And then we're going to calculate the total power produced, the net power produced by the cycle. Okay? So that's the plan for today. I think I better actually start writing some assumptions down. I've gotten lazy about this the last several lectures, so hopefully we'll get back to writing some assumptions down. Okay, so let's get started here. Let's calculate the specific pump work. Let's calculate the specific pump work here. So, analysis. So I don't know anything about state 2. I do know, except pressure. I do know at state 2 what the pressure is, but I don't know what the enthalpy is at state 2, which is the pump outlet state. So I know what the pressure here is at state 2. It's 6 megapascals. I know what the initial pressure is. I know it's a saturated liquid, so I can't get an inlet enthalpy. I could do that. But I don't know anything about state 2 except pressure. I need two properties to get an enthalpy so I can apply the energy balance and get a specific work. So what I'm going to instead do is what we usually do. We're going to use the definition of isentropic efficiency. So the isentropic efficiency of the pump is equal to the specific work or power. You could do W dot for the isentropic pump divided by W for the actual pump. Remember, in this context, the isentropic pump is actually the reversible pump. Okay, so what I really mean by this is W dot reversible pump. That's what I mean. Okay? Okay, so that means W pump, the specific pump work, is equal to the isentropic pump work or the reversible pump work divided by the isentropic efficiency of the pump. Okay, now we already have an expression for isentropic efficiency for the pump. So we developed this last time. That's the specific volume of the saturated liquid times the delta P. So that'll be P2 minus P1. We developed that expression for isentropic or reversible pump work, if you like. We developed that expression last time. So I have a specific volume of the saturated liquid. Let's see here, that's going to be evaluated at a pressure P1. So pressure P1 is 7.5 kPa. 7.5 kPa. Pressure 7.5 kilopascals. And then I have a delta P. Let's see, P2 again is 6 megapascals. And P1 is 7.5 kilopascals. 6 megapascals minus 7.5 kilopascals. Okay? So this is 6 megapascals minus 7.5 kilopascals. So obviously got to do a unit change there. So there are 1,000 kilopascals per 1 megapascal. Okay. So 6,000 minus 7.5 kilopascals. All right, we crank through and we find that the isentropic work is 6.04. I'm sorry, what's the isentropic efficiency of the pump? 80%, so 0.8. So we get 6.04. Let me check this one more time. Isentropic pump work was 6.04 or 6 kilojoules per kilogram. 6 kilojoules per kilogram. And I get 0.8. And I get what? 7.2? 7.2. I'm sorry, 7.55 or 7.6 if you like. 7.6 kilojoules per kilogram. By the way, I didn't write it up, but I got from tables specific volume for the saturated liquid evaluated at 7.5 kPa. Might have to do a little bit of interpolation there using the tables that you have. Let me write down the specific volume here. It is 1 times 10 to the minus 3. Actually, not much interpolation there. So 1 times 10 to the minus 3 cubic meters per kilogram. And that's from tables. Okay, that's from tables. Okay, so W pump is equal to 7.6 kilojoules per kilogram. 7.6 kilojoules per kilogram. Let me write that over here. W pump 7.6 kilojoules per kilogram. Okay, that's the specific pump work. Good. Now let's calculate the specific turbine work. Oh, I'm sorry, I forgot to put one item in here. I just realized it. The maximum temperature in the cycle, T3. Maximum temperature in the cycle, T3. That is 1,092 degrees. Sorry about that. Let's see here. T3 equals T max equals 1,092 degrees Kelvin. Sorry about that. So just thinking I need to know my state 3 to get a pump work. I'm sorry, to get a turbine work. So I need to know something more about state 3. Okay, let's calculate the turbine work. Let's calculate the turbine work. So that's going to take a little bit more effort here. So let's use the isentropic efficiency for the turbine. So isentropic efficiency for the turbine is mass flows are the same for the isentropic and the non-isentropic. So that's the specific work for the real turbine divided by the specific work for the isentropic turbine. So W turbine is equal to the isentropic efficiency for the turbine times the isentropic turbine work. Okay, I have the isentropic efficiency for the turbine. Let's see, what is it, 85%? 85%, okay, so I got eta turb. I got eta turb, very good. Let's find the isentropic, let's find the work for the isentropic, specific work for the isentropic turbine. So again, let's look at process. The turbine involves expansion from the boiler outlet to the inlet of the condenser. So state 3 to 4, and this is for the isentropic device. So we're going from 3 to 4 sub s. 3 to 4 sub s. Process. 3 to 4 sub s. Isentropic expansion in the isentropic turbine, okay? Apply the energy balance. I guess I better write in the assumption, I'm assuming my pump and my turbine are adiabatic. Adiabatic pump and turbine. Okay, adiabatic pump and turbine. Else, got to get the first law right. Let's see, W, mass flow rate. I'm going to factor out the mass flow rate, and I get W turbine, and this is for the isentropic turbine, is equal to H3 minus H4 sub S. Okay, now what's H3? So H3 is H evaluated at pressure P3 and temperature T3. Let's see if I have these temperatures and pressures. Let's see here, at state 3 I have a P2, which is P max, that's 6 megapascals. I don't see any indication there's a pressure drop across the boiler or the condenser, so I'm going to write here in the assumptions delta P from 2 to 3 and delta P from 4 to 1 equals 0. These are isobaric boilers and condensers. So this means that P2 is equal to P3, and that's equal to my maximum pressure, so 6 megapascals. This is my pressure up here, 6 megapascals. P3 equals 6 megapascals, and P4, by the way, is 7.5 kilopascals. P4 equals 7.5 kilopascals, by the way, okay? So P3 is 6 megapascals, and T3 is 1092. 1092. 1092. So 6 megapascals and 1092 degrees Kelvin. You're going to find that you're in the superheated vapor region. You're going to find that you're in the superheated vapor region. And I get a specific enthalpy is 4856. 4856 kilojoules per kilogram. You're going to find that you're in the superheated vapor region. So indeed, this TS diagram, I drew it correctly the first time. You have superheat all the way up here. So So T3 is 1092 Kelvin, okay? So it's a superheated vapor. Superheated vapor, okay? By the way, the specific entropy at state 3, let's see if I can find it here. Specific entropy at state 3. Oh, did I write it down? Yes, the specific entropy at state 3 is 8.2. So S3 is S evaluated at P3 and T3. That is equal to 8.25 kilojoules per kilogram degree in Kelvin. Okay, that might be important because we have an isentropic process going on here. Okay, so I have H3 now. So what's H4 sub S? H4 sub S is equal to H evaluated at pressure P4 and specific entropy S4 sub S equals S3. And S3, of course, is 8.25 kilojoules per kilogram degree in Kelvin. Okay? And P4 is equal to the condenser exit pressure. Condenser exit pressure, which is 7.5 kPa. 7.5 kPa. kPa. So that specific entropy is 2574.8. 2574.8, or if you like 2575 kilojoules per kilogram. State 4 turns out to be a saturated vapor. So 4 sub S is a saturated vapor, okay? So hopefully my TS diagram, do I have that right? I should put the TS diagram, the state 4 sub S there. So 4 sub S turns out to be a saturated vapor, okay? Saturated vapor. All right, so I have H4 sub S now. And so I get 4856 minus 2575, and that's all in kilojoules per kilogram. And I end up with, let me crank this out. Where's my calculator? Here it is. And I get a specific work for the isentropic turbine, 4856 minus 2575. And I get 2281 kilojoules per kilogram. 2281 kilojoules per kilogram. Okay? Okay, so now I have the specific work for the isentropic turbine I can plug in. Let's see here, 85% efficiency, 2281 kilojoules per kilogram. So times 0.8, make sure I have the right isentropic efficiency. Yes, I do. And I get 1938, actually 1939 kilojoules per kilogram. So the work of the turbine, specific work of the turbine, is 1939. W turb 1939 kilojoules per kilogram. So I'm going to box that up too, okay? Box that up too. All right, well, good. Now we can immediately calculate the net specific work, which is the difference between the power produced or the specific work produced by the turbine and that consumed by the pump. Okay, you have to drive the pump, so I need to subtract off about 7.6 from the 1939. Okay, so let's do that. So W, note, W net is equal to the specific work of the turbine minus the specific work of the pump. So that's going to be equal to 1939 minus 7.6. I'm going to do some rounding here. 7.6 kilojoules per kilogram. And I get, whoops, minus 7.6. And I get 1931 kilojoules per kilogram. So the net specific work is equal to 1931 kilojoules per kilogram. Okay, that's that right there. Let me put that up right over here. 1939.1, 1939.1. Oops. 1939.1. W net equals 1939 kilojoules per kilogram, okay? Okay, so that's that. Check, check, check. Let's find the heat addition to the boiler. Let's find Q to the boiler, that's per unit mass. Let's find the heat addition to the boiler. Well, application of the energy balance over what process? Well, from the boiler inlet to the outlet, let's see here. I don't know if I turn it so quick. So apply the energy balance to the boiler. So that's from state 2 to state 3. Apply the energy balance. There's no work interaction going on. I get Q dot boiler equals equals M dot for the H2O, H3 minus H2, or if you like, Q boiler equals H3 minus H2. Now I have H3 somewhere. There it is, 4856. So what's H2? I don't know what that is. Let's apply the energy balance to my pump. So process 1 to 2. So this is the pump work. So let's apply the energy balance to our pump. The pump has no heat interaction going on, so I have W dot pump is equal to M dot for the H2O times, okay, where's the inlet and where's the outlet? Let's go look at our diagram. Inlet's 1, outlet's 2, so H2 minus H1. Whoops. H2 minus H1. Or in other words, W pump is equal to H2 minus H1. Or in other words, H2, that's what we're looking for, is equal to H1 plus the specific pump work. Now I have the specific pump work, we just calculated, it's like 7 point something kilojoule per kilogram. I don't have H1, but I can look it up. Let's see, H1 So H1 equals H of the saturated liquid evaluated at a pressure 7.5 kilopascals. So state 1 is a saturated liquid. State 1 is a saturated liquid. That's pretty easy to do. I can look it up in a saturation table. And I find H1 is equal to 168. It's actually 169 kilojoules per kilogram. Equals 169 kilojoules per kilogram. Okay, that's from a table, interpolated from a table. Okay, now I have H1. Check, excellent. Let's see here, 169 plus the specific pump work, 7.6. And that has units of kilojoules per kilogram. So basically, I'm just going to round up here. This is 177 kilojoules per kilogram. 177 kilojoules per kilogram. Okay, now I have H2. In fact, I'm going to write that somewhere. Write it right up here. Sorry. H2 equals 177 kilojoules per kilogram. Okay, I'm going to write that up there. Okay, right. So H3 is 4856, and H1 is 177 kilojoules per kilogram. And I get a specific heat addition in the boiler. 4856 minus 177, and I get 4679 kilojoules per kilogram. So the specific heat addition in the boiler, Q boiler is 4679. Q boiler equals 4679 kilojoules per kilogram. Running out of space here, running out of space, as usual, as usual. Hard to do these problems with only 2 small blackboards. Okay. Okay, so let's calculate the thermal efficiency now. I have the specific heat input to the boiler. I have the net specific work. I can easily calculate the efficiency. Let's do it. Efficiency. So the efficiency of my cycle is equal to the net power divided by the heat addition in the boiler, rate of heat addition, dividing through by the mass flows. Mass flows all the same through the cycle. I have W net over Q boiler. W net was 1939. And Q boiler was 4679 kilojoules per kilogram. All cancels. And I get an efficiency. I get an efficiency of 41%. 41%. 41%. So this thing converts 41% of the heat added in the boiler. 41% of the heat added in the boiler gets converted into usable work or power. So eta equals 41%. 41%. Running out of room, gonna have to write it somewhere else, okay? Let's calculate the mass flow rate of the working fluid, the H2O, as it rolls around the system. Now, one thing I am provided here, it's simply given, but I should write it right here. The rate of heat addition to the boiler is actually 40 megawatts. Well, I know the specific heat addition, Q boiler, lowercase q boiler. I know the rate of heat addition, Q dot boiler. I can immediately calculate the mass flow rate through the boiler and everywhere else. So we have Q dot boiler is equal to the specific heat addition in the boiler times the mass flow rate of the H2O through the boiler and through every part of the device. So therefore, m dot H2O, the mass flow rate of the H2O around my cycle is equal to Q dot boiler divided by Q boiler. Oh, Q dot boiler is 40 megawatts. I'm going to have to convert that into kilowatts, so that's 1,000 kilowatts per megawatt. And then I'm going to divide that by the specific heat addition of the boiler, which is 4679. 4679 kilojoules per kilogram. Again, the kilowatt, so the megawatts cancel, and a kilowatt is a kilojoule per second. The kilojoules cancel out, and I get kilogram per second, which is exactly what I want. Let's see here. Let's see here. I get 8.5 kilograms per second. 8.5 kilograms per second. 8.5 kilograms per second. So m dot H2O equals 8.5 kilograms per second. Yes. Okay. 8.5 kilograms per second. Ooh, I don't know where to write this. Let's put it in the diagram. Let's put it in the diagram. So m dot H2O rolling around the system is equal to 8.5 kilograms per second. Okay? Check, check, check. Let's calculate, finally, let's calculate the power, the net power output for my cycle. Let's calculate the net power output. Well, there are a couple of different ways to do this. I can use my thermal efficiency, or I can use my m dot and my W net. Let's use the m dot and the W net. So W dot net is equal to W dot turbine plus minus W dot pump, which is equal to m dot H2O times W turb minus W pump. And of course, this is W net. That's W net right there. So I get m dot H2O, W net, so 8.5 kilograms per second, and my net specific work is 19.39 kilojoules per kilogram. 1939 kilojoules per kilogram. Kilograms cancel out and I get kilojoule per second, so I'm going to get kilowatts. Probably want to convert that into megawatts. Probably want to convert it into megawatts here. Oh, what did I do with my calculator? There it is. So 8.5 times 1939. 1939 times 8.5. And I get 1648 something. Let's see. 1648, and that's kilowatts. Let's convert that into megawatts. So for 1 megawatt, there is 1,000 kilowatts. Kilowatts cancel, and I get 1.648 megawatts. So W dot net, the power produced by this power plant is 1.648 megawatts. 1.648 megawatts. W net 1.65485 megawatts. So 40 megawatt, oops. Did I make a mistake here? That can't be right. Q dot boiler is 40 megawatts. Let's see here. No, I got 16. How did I make a mistake here? M dot. Oops, let me check my calculator one more time. That's not right. It should be 16. And it is 16.4. Sorry about that. There should be a 1 here. Sorry about that. 1 kilowatt. So I get 16.48. If you like 16.5. So this should now be 16.5. So sorry about that. 16.48, 16.481, 16.48. Sorry about that. Made a little mistake on the calculator. And I get 16. I'm going to round it up to 5. 16.5 megawatts. So 40 megawatts goes in, heat added in the boiler. 16.5 megawatts comes out in the form of work. The rest of it is rejected. By the way, I can immediately calculate the condenser heat rejection. That's going to be 40 megawatts, what goes in, minus what goes out as work. 16.5 megawatts. Looks to me like I have 23.5 megawatts. If you want to know what the heat rejection is at the condenser, 23.5 megawatts. Okay? Q dot boiler minus W dot net equals Q dot condenser, 40 minus 16.5, 23.5. I think that's right. All right, ladies and gentlemen, that's a fairly decent problem. Take care.